host Rim Barty with my co-host Joseph-Celestine Donald, together representing the South Tunisia and Benin SOLIDWORKS User Group. We are going to take your assembly skills to the next level. Today, we'll be breaking down everything from the fundamentals of the assembly environment to advanced motion study. So, we'll be sharing some key insights. Get ready for deep dive into the world of affection and intelligent assembly design. And thank you for your join. Before we dive into the technical content, a quick button to join down the key point. And please hold all your questions until the end of session. We have reserved ample time for your comprehension question. Thank you.
Okay. Hello, everyone. Please indicate if you can hear me.
Yeah, we can hear you.
All right. Thank you guys for joining today's session. So I'm sure more people will continue joining as we progress. Okay. So my name is Joseph-Celestine Donald. Uh, I'm a certified SolidWorks professional, and I've been freelancing since 2021. After I was sure I was good with SolidWorks, then I also serve as the leader of the Benin SolidWorks User Group, then also the media manager for Lagos SWUG User Group. I just help promote technical education and professional engagement there. Then I was I had the opportunity to serve as the former director at IDEA, International Designers and Engineering Alliance. Then recently my design was ranked top 30 in the SolidWorks at 30 competition. Then also I co-founded a mechanical design company, MKV Consulting. Then I'm a student member of the Royal Institute of Naval Engineering Architect because I studied naval engineer and marine engineering at university. Then I'm certified in 17 plus SolidWorks and 3D experience modules. So for me, engineering is not really about just the software. Okay? It's more about problem solving and design intent and thinking. Okay, so it's a pleasure to have you guys here, and I hope we have the best of times. Thank you.
Okay, thank you, Judith, for your presentation. We are happy for your present today. And I am your host, I'm Jim Batki. I'm a mechatronics engineering student at ETH Jerba. And I am ambassador for the South Tunisia SWUG. Also, I'm intern at Abibika Physics Works. At first, my experience has followed my passion for applied mechanical design and system integration. Like Donald, I'm deeply involved in my SolidWorks community, and I believe that knowledge sharing is key to innovation. I'm also certified in 14 SolidWorks and 3D experience mode, and I hold my CSWP as my certification professional.
Okay. Once again, thank you guys for joining. So today the main aim for today's session is basically to give you a structured approach to SolidWorks assembly. So let me begin by introducing the SolidWorks assembly interface. This environment here is much more than a workspace, right? Now, if you've used it before, you can say, okay, this is the command center where individual components are actually transformed into real life products. So it's quite important to vision and imagine the SolidWorks uh, assembly interface as your workspace, like your physical workspace where you carry out all your uh, assembly and your fit and your testing and so on. So on the left hand side, we have the begin assembly tab, now highlighted in red. This is where basically our entire workflow starts, because this is where you import your parts into SolidWorks. So it's good to note that immediately you import your any part into SolidWorks at first, that part is fixed. This is invariably uh, because to avoid floating parts, your parts has to be fixed and stationary. So more like keeping your work on a bench or a bench vise or something, clamping your uh, first component to something so it doesn't float. Then now moving on to the yellow box, we see the feature manager design tree. Now the feature manager design tree at default will replace the beginners assembly tab at default because it stays there. Then yes, uh, this is where you actually get to see all your inserted parts, where you see your mates. So it more like acts like a timeline where your design based on hierarchy, depending on which one you first added, it's all pops up there. Then also, if you have an error, that's where you actually go to kind of like diagnose the whole thing. Then so basically what it does is it just gives you full control over the more logic structure of the assembly. So more like in a complex system where you have thousands of parts, it's more like your guide where you can see all your designs fully displayed. Then in middle you see the graphics interface for SolidWorks assembly, right? So the graphics interface primarily is where our 3D workspace, where everything we do is basically carried out. So uh, here you can actually just import your parts and then you start working. So more like this is where your main work is actually being done. Then the next tab in blue, there you see it's the heads up view toolbar, right? So this is just basically for efficiency's sake. Now, any of those tools you see there can easily be gotten from the either the add-on or you just search it out, right? But for an engineer, it is quite important that efficiency is one of the core things or the core values you should hold, because designing, as we all know, has to do with both time management and then both being efficient, right? So most of the tools there are just basically to make your design process and then to make your whole easier. Okay. Then at the bottom of the screen, we'll see the motion study tab. Now, it's also important to note that for most of your designs, right? For most of your designs where you have to hide certain parts, where you have to take up on, let's say, complex design. So the whole combination of the whole combination of the tools you have at your disposal matters, right? So then these parts are also customizable, including the tabs and all that. So for me, like if I install SolidWorks new for the first time, I must customize my whole interface, right, for it to suit my hand, because I now have this muscle memory where my hands go if I need a certain tool, right? If I need smart dimension, I have a place where I put it, so I don't really stress that much and move all that. Then back to the last one, that's motion study, right? Then motion study basically, so since we'll be talking about motion study as we progress, I won't go much into it, but basically the tab there, not only motion study stays there, if you're conducting a simulation, if you're conducting a simulation, it pops up there too. Then also, yeah, that's where your static, not flow simulation though, only static simulation shows there. Why for flow simulation is the same place where your configuration tools are, where your configuration tools, your appearance, yeah. Flow simulation shows up there, the flow wizard rather. Then so basically then you now have the colors. This is where you input your colors. Now of course we should know the difference between adding colors and then adding materials, right? because adding materials gives you the actual and the structural density of that material. It gives you the properties of said material. Then adding just appearance is just for the color sake, right? So you can't actually say you've added material because you added color. Now, a material can look different from a color. So you can actually have an appearance of plastic, but actually the material is stainless steel. So you have to be careful. And then when it comes to adding of material or color on SolidWorks assembly, it's quite important to note that you have the option of choosing either to actually change said color in just the appearance and then leave the part at default how it is, or you can actually just change both sides at the same time. So overall, at the end of the day, this interface is basically not just a software, right? It's more like a digital laboratory or your own workshop, personal workshop, like how real life you actually have to couple each component one by one, because overall there are no actual parts or system in the world that isn't made up of parts and then assembly. So assembly is quite important, and then it's basically bridges your own theory and then bridges it with the much more mechanical aspect and a much more realistic and physical aspect of the whole thing. All right. Okay. Thank you. Then okay. Now, now not even one of the most important. I would say the most important aspect in SolidWorks assembly is mates, right? So at default, there are four types of mates. And default, then depending on how much you've used SolidWorks, depend on the range of how much you used, right? Now, in fact, the core logic, actually, the whole logic of um of an assembly depends on how much your mating strategy works, on how much you are able to manipulate or use mating system, right? Okay, now because the main idea in mating is not really to constrain alone, right? Is to constrain with purpose. Okay. Then then now if you ask for a proper definition of mate, a mate defines the geometric relationship between components in an assembly. So if in my opinion, the way I view the whole idea about mating is I feel it much more physical, right? You have I assume the mate to be a bunch of tools I can use to assemble. So it's either I'm using my nut or I'm using a glue or I'm just sticking it together. So at the end of the day, you should picture using the mating tools as like you're using it in real life, right? So then first, we have the standard mates. So basically, these are just functional geometric constraints. They are one of the ones we use much more frequently in assembly. So what they include are the coincident, the parallel, the concentric, the perpendicular, the distance and the angle mates. Now, the distance and the angle mates now varies because the distance and the angle mate appears twice. It appears both in advanced mates and then it appears in standard mates. In standard mate, it is just a distance fixed, while in advanced mate, it is more like a range, especially if you're working with let's say hydraulics, right? Where you have to make or robotic arms where the angles of each link actually is very very important. Okay. So, for example, let's say we have a cylindrical body, right? And then we meet said body into another cylindrical hole. Now we've added concentric, all right? Then if we join two faces together, we've added coincident. If we make, let's say you imported a component and then it was healed or bent or tilted a little bit, and then you actually straight it up perpendicular to the fixed or the first one, you've already okay. So what I'm going to do is this: I'm going to share my screen so you can see a little bit of what I'm talking about. Okay, please let me know if you can see my screen. Yeah, hello, please. Can you see my
Yeah, we
screen?
can see.
Okay, all right, thank you. Now, Now, as far as mates go, now I want you to picture mating as one of more like real life, right? So I go to my mates and then I'm just going to briefly explain so we don't take up much time. Now, like I said, standard mates. For standard mates, you have coincident, right? So basically, coincidence is you joining two faces or two edges together, makes it coincident, right? Then we have parallel. Parallel, it keeps them at the same line. They all share the same heel or the same angle if it's at angle 90. One of the parent mate and the child mate, one of them turns now mimics the position of the other, right? Then we have the perpendicular, basically how perpendicular actually works. A line should be angle 90 of the horizontal or the vertical line it's being perpendicular to. Then we have tangents. Tangents are for circle and edges, or circle and cylindrical, right? That's for tangent. Then concentric are for two cylindrical bodies. All right. So perfect. Now that's just it. So at the base level, the reason I don't think there's too much to it is this, because since it's a matter of choice, right? Since how you assemble a certain part or a certain product is based on whatever it is being applied to, right? So it means you now have the prerogative to do whatever you want to do with it. You can use the assembly, you can use any meeting you actually want to, as long as it is logical for that purpose. Okay. Then now we move to the advanced mate. This is where basically we use these are just the relationship between parts. Advanced mates are mostly relationship between parts, if and are parts that are much more complex. Now, for instance, the most popular advanced mating we use out there is the weighted mating, right? Is the weighted let's see, advanced is the weighted mating, right? Now, the weighted mating is one of those mates that just keeps it middle. What it does is this: weighted mating works with two parts rather, right, and keep it at an equal distance. Then same with symmetrical, but the only difference between the symmetrical is that the symmetrical works with only planes. Okay, so symmetrical basically means you put in your object or your part or your component middle at an equal distance from a certain plane. Okay, then we have the path mate. Now, if you've taken the CSWP exam, you'll notice that at the end of the CSWP exams, the robotic arm, yeah, I think that's one of the most useful uses of the pathmate. But then again, we have situations like if you're working on a Formula One, let's say you're working on a race car, and then you have to make it move around the path, mostly for demonstration, or you want to actually perform a crash test. So you use your pathmate. Or okay, like when I was working on a recycling machine, a plastic recycling machine, where the debris had to go alongside the conveyor belt, right? So at that process where I had to use part mates, so I had to use an helix with different pitch and different revolution, and then an object, and then run it through the part mode. So part mode takes it through the whole what do you call it? So part mode just basically follows the certain part or the line you've actually done. Now, another use for PadMate, I think, would be this photorealistic rendering in motion study, camera view in motion study. So, if you want to perform camera view in motion study, lights and camera in motion study, right? So here you use your, especially if you want to make like all these 360 views and then inside and out of your assembly, okay? Especially if you're actually presenting, let's say something like a car or a product that needs that you basically just like that be moving your camera. So yeah, the part mates actually helps. Then we have the mechanical mates. Okay, the mechanical mates are the most important mates a mechanical engineer should have. But at the same time, the mechanical mates just basically represent real life objects. Because if you notice for the mechanical mates, there you have hinges, you have hinges, right? Then you have the gear mates, you have the rack and pinion, you have the screw, and then you have the universal joint. But basically, at the end of the day, now for instance, the rack and pinion mating can still be done with the gear mating, but just for efficiency's sake, it's there. Then you have the cam. Now, if you know how an engine looks like, you know the camshaft in an engine. So the engine itself needs what do you call it? So the camshaft. So instead of you actually just using a tangent mate on it, you now have a cam mate. Then especially if you're working with belts and chains. Okay, so those are cam movements that you use cam your cam your cam mates for. Okay, then hinges are specifically for hinges, doors. So at the end of the day, every system you're building, especially if it's a massive system, should have a door. It's either you're building automobiles or you're building aeronautic devices. Whatever it is, must have a opening of some sort. It can be a door, it can be a window, it can just be a compartment opening. Okay, so basically these parts are just extremely important, especially when you're designing mechanisms like a gearbox or linkages or an automated system, right? Good. So then, lastly, we have the what's it called? We have the smart meat. Okay, smart meat is the smart meat. Now, when it comes to the smart meat, what it does is this: it anticipates your. Sorry, give me a minute. Hello, can you hear me, please?
Yes, yes, we hear
Okay,
you.
all right, thank you. Now, the smart mate, what your smart mate does is this. At default, let's say at the most default level, the smart mate is basically it anticipates the best possible mating to be used for that said purpose. For instance, you bring two holes together, and then the first thing that comes in mind, it ranks it is okay. I think concentric is the best rather than tangent, right? So it basically depends on what it actually. It's called the smart mate. So I assume I don't use it much because especially when you want full control of your design, right? Okay. Then the last one is not really a mate. So that's why I said there are four types of mate. So the mate expert is more like a diagnostic tool, right? So what it does is it's more like a diagnostic tool. When I say diagnostic tool, you should know it helps you detect errors. When you have errors, when you either your design is over constraint or your design is under constraint, right? So when you have a problem like that and you can't really find what the issue is, okay? So what this does is it actually sorts out that issue and then tells you this is what is wrong. Is either you are over defining a certain mate or you broke a certain mate. So basically just like that, and then you can now be able to fix. So in summary, what I'm trying to say is that matings are what I'm trying to say is this that matings are um, kind of like the foundation of motion control, right? And then structural integrity. Okay, so when you apply your mates properly, paying attention to actually mechanical factors like your degrees of freedom, if it's properly mated. So the main idea, like I said earlier, is not just to mate your design, right? But to actually mate with purpose. Okay, all right. Okay, now we've talked about mating, right? We've talked about the different kind of mates we have, right? So what I'm going to do is this: I'm going to share my screen, and then we're going to assemble an inline engine, a four-cylinder inline engine. Okay, so what we're going to do is this: we're going to any mates we apply, you're going to see, and then you should know this when it comes to assembly, there are quite a number of ways you can actually mate your designs, right? So you just have to choose the best possible process. I call it a process, the best possible process to come up with your assembly at the end of the day, and then efficiency too, right? Okay, so I'm sharing my screen now. And also, please, if I'm too fast, just let me know. Thank you.
So please, the times, Joseph, go to the SolidWorks, join our community. You have the link in our chat. Thank you.
Okay, let me know if you can see my screen, please. Can you see my screen?
Yeah, it's clear.
Okay. All right. Now, okay. Now, so not so I don't sound so everything I say doesn't isn't just theory. We're going to work with the same process, same way I explained how mating is. Now, I said the first thing I said is this: your you can start anyhow you want to assemble, but we should picture it like real life, right? Okay, now here's my thinking, here's my process. Now I think, okay, we're designing a four-cylinder inline engine, right? And then this engine, if you're a mechanical engineer or a mechatronics engineer or an engineer, you should have seen at a let's say a simple engine should have a piston, should have a piston ring, it should have a connecting rod, it should have an engine block, right? Then it should have a crankshaft and all that. Okay. So then what I'm going to do is this now. Since we know since we know our piston is going to be since we know our piston is going to be a piston on its own. So what we'll do first is we assemble the piston separately, then we assemble um the whole components together. Okay. So then first things first, I insert my component, then I browse through my components. Okay. Then I select the connecting rod. Then at default, at default, at default, this is fixed. Okay. So I right click and I float it. Okay. Perfect. Then now it's floating. Okay. It's floating. Now I said, let's picture this like a workshop, right? If we're working on a workshop, our design shouldn't be right. It shouldn't be just on an empty space. So what I do is this: origin, the origin of my design interface and the origin of my first part, and make them coincident, right? Doing this now, my front plane or the top plane of this part now aligns properly with this part, with the top plane and the front plane of the assembly canvas. Okay, perfect. Then I insert the I insert the connecting rod cap. Okay, okay. Then easily I take here. Now, okay, what I'm going to do is this. I'm not going to go here and start using mate because it's going to take a lot of time. I'm going to click the part I want to mate. I hold control and then I select the second part I want to mate, right? Okay, then the option for which of the mates I want to use. If you hover over them, you get to see the options. I think it makes my work much more efficient. Okay, so here you have the parallel, you have the perpendicular, tangent, and then these are basic. If you notice, these are basic, these are standard mating. Then you now have an advanced mating, these two, right? Good. So I make here concentric. Then I take here and I make here concentric. Coincident, right? Good. So I insert the part. So I insert my bolts, I insert my nuts. I'm selecting them so I can insert multiple times, multiple components I need. I need the bolts, I need the nuts, then I need my piston, and then I need my piston ring, and then I need my piston pin. Okay, so I open them and I start dropping them separately. Okay, good, perfect. So first things first is here. Okay, perfect. So I'm going to bring the knot closer. Then, okay, then first things first. First things first, I'm going to use here and here, and I'm going to give it a distance of 10, right? Good. Then I'm going to apply. Now, why I'm doing this is because I want to apply an advanced mate, right? So I'm going to go to my mate. I'm going to select advanced, sorry, mechanical rather. And I'm going to select screw. So for the screw mate, I'm going to select this face. Then in the knot, I'm going to select this face. Now it now tells you the direction of your, so you have a whole lot of option, how many revolution per how many the distance per revolution covered and all that. So we're just gonna leave them at default and say okay. Then I'm gonna shift it. Right, good. So then before anything else, I'm going to right click this component and I'm going to copy with mate. Then I'm going to select this set component too. Then so copy with mate makes your designing process much more easier if you've used it before, right? Especially if you don't want to use linear pattern. Okay. No. Okay, good. Then cancel. So I'm going to make here and here. I'm going to make it at a distance of 8. Okay, good. Then I'm going to make here and here. I'm going to make them parallel. Sorry, coincident rather. They're already parallel. I'm going to make them coincident. Okay, good. Perfect. Then for the piston, I'm going to add the rings. So if you're a mechanical engineer, so I'm adding this, I'm adding the ring. So I want you to, on the comment section, I want you to tell me why as an engineer we need to use, we are adding this piston ring. Why is the piston ring, this ring here, important in this internal combustion engine? Okay. Okay. All right. Perfect. So all I have to do is take here and make here concentric. Then I'm going to take here, here, and here. And then I'm going to make them, I'm going to use the with it mate and keep it midpoint. Good. Okay. I'm going to apply another with it mate. With it mate only works with face. It doesn't work with edge. So if I were to select another edge instead of a face, it wouldn't work, right? Okay. All right. Perfect. Now we've okay. Now we've assembled the piston. Okay. So what I'm going to do is I'm going to save the piston. I'm going to save it as a separate document, right? I'm going to say P. I'm just going to save it as P. Okay, good. And then I'm going to Control N. I'm going to open a new assembly. So now for this assembly, like I said, every single individual assembly you open, every individual workspace you open is a physical workshop, right? Separate on its own. So this is another workshop. So what we do is this: we're going to start inserting. We're going to insert, let's say, okay, let me start with the engine block, right? So since it's the biggest component there, so then you can start with the crankshaft depending on what you want, right? So I've inserted the engine block, okay? Okay, so then of course we know it's going to be fixed. So I'm going to right click and I'm going to make it float. Then I'm going to constrain its origin with the origin of, right? Perfect. Good. So then I'm going to insert the crankshaft. Okay, so I'm going to take here and make here concentric. Good. Perfect. So now this let me explain something a little bit. We'll talk about it later then, but this crankshaft, right? When I first inserted the crankshaft was actually it had 6 degrees of freedom, right? It's floating in space at default, so it's really not moving, right? Then immediately I add the concentric mates. I've now restricted on purpose and with purpose the let's say I've restricted the movement this way and this way, right? So what I've basically done is this. In the x direction, if you could look at my if you look at my triad here, you can see that in the x direction, I've already restricted it from moving this way and I've restricted it from moving this way, right? Good. But it still can move this way and then it can rotate on its axis. Okay, good. So I'm going to insert another component. This time I'm going to insert the assembly we did just now, right? Good. Now, okay, I don't know if you know this, okay? If you insert a part, if you insert now, key things. One, if you insert a part into SolidWorks assembly, a first part, it is fixed. Now, if you insert a subassembly into SolidWorks, your subassembly is not fixed, but your subassembly is what's the word? Rigid. Okay? Rigid. When I mean rigid, I mean it's not fixed, right? But any mate that was applied, any movable mate, especially concentric, now ordinarily this part should be rotating, right? But it's fixed. So the whole sub-assembly is rigid until you make it flexible. Now the purpose is this: for large assemblies that have much more moving parts, when you import, for instance, you're working on a power plant design, right? And then you've done where you have multiple sub-assemblies and then you now import in a new sub-assembly. If that sub-assembly comes with all its mates, this space is going to be filled up. That's one, and that's not the only thing. Then your rebuilding time, especially if you have designs up to like 1,000 or 500 components. So the rebuild time begins to actually, it takes longer to get to rebuild. Okay, and then if you make an alteration or an edit or a modification up in the hierarchy, it takes a lot of time for it to come back. And most times, if your laptop is not really that strong, it ends up crashing, right? So what we are going to do is this. So I'm going to right click on the component and then I'm going to make it flexible. Okay. So when I make it flexible, it loads and then these parts can now move. So it can now move freely, right? Good. So this is what I'm going to do. I'm going to rotate it. Okay. I'm going to make here. I'm going to make here and here. I'm going to make here and here. I'm going to make them concentric. Right. Good. Then I'm going to take here and I'm going to make here and here. I'm going to make it concentric. Okay. Perfect. So perfect. So then what I'm going to do is this, I'm going to right click and then I'm going to copy with mate. Okay. Then I select this place, concentric, and then second concentric. Okay. Okay. Then immediately I'm going to make the said sub assembly what? I'm going to make it flexible. Okay. Good. So I'm going to do the same thing. Right click. I'm going to copy with mate. Now you can copy with mate, you can use linear pattern, but using linear pattern you have to know the exact distance between each of these parts, right? The distance between the center or the axis of this cylindrical hole and that of the next one, and then you can then apply simple linear pattern mate. Okay. Then I'm going to make it flexible again. And then I'm going to do the last one, and then we're done. I click and then copy with mate. Okay. Okay, now perfect. Now, but note, this part is still not constraint, right? So what I'm going to do is this. I'm going to take here, I'm going to take this edge, and then I'm going to make it coincident. And just like that, our design is fully constrained. Okay, let me see. It's fixed. Okay. Now, okay, good, perfect. Now, the whole process.
Thank you, Joseph. We hope everything was clear to everyone.
Okay, all right. So, okay. Now you should know the whole assembly process, like I said, mimics real life. All right.
All right. Once our assembly is real, the next logical question is, does actually move the way intended to? We see the motion study. So this is where motion study come in. SolidWorks provide 3 levels of motion study. The first is animation. It's available in core SolidWorks. It's great for creating sample turntable animation or exploding views. The second is the basic motion. It's available in core SolidWorks, and is basic motion allow you to approximate the effect of motors, spring, and gravity for visualization purpose. But to truly simulation and analyze the real-world physics of your mechanism, included force, friction, and damper, this the rule of motion analysis available with SolidWorks Motion and into SolidWorks Premium. So we can here directly practice your motion. So we go. So just a moment. You can see my screen.
Yes, we can.
Okay, so here our assembly. Just go to motion study here, and we must choose our motor. And the front of the motor, we have we should define 3 things. The first is the emplacement of the motor. Okay. The second is the direction, and the third is the motor. Here we choose the crankshaft as the motor because it's the part who has the movement. Okay, so we choose use the crankshaft as the motor for the direction. This the face of entry is the direction and the emplacement. As you can see, this is our motor, the crankshaft, here because he has the movement of rotation. here the emplacement of the motor, because the crankshaft is in the block motor, and here our direction. So after we confirm it, the motor, and we played our animation. As you can see here, our movement here. It's clear. As you can see there, the internal combustion engine works perfectly. You can repeat it. The piston move up and down, like we see. We can control for the type or for the animation, speed or slow. Okay. For understood this mechanism, the system, when the internal combustion engine works perfectly, the piston moves up and down, like we see. The cylinder converting the fuel and into the mechanical, and the crankshaft rotate smoothly. I hope this is clear. Any question? So we will back to our presentation.
So, okay. So now for for to be an engineer, right? We should avoid just being on the creative side whilst actually neglecting the most important and the fundamental parts of being an engineer, right? Now, it's okay. To my question, Promise got it right. The purpose for the they both got it right actually, but the primary purpose for the ring is to seal off the combustion engine from because it uses lubricating oil, right? So if it's not properly sealed, smoke escapes from the combustion chamber down into the oil, and then it contaminates it. That's where situation where you now start having black oil. Okay. Uh nice one. Then also okay, now it's very important to understand degrees of freedom. Okay. For these degrees of freedom, so we understand it properly and in a much more simpler way without the whole bricky grammar, I'm going to explain it in a simple manner. Now, first, degrees of freedom and mates go hand in hand. All right. Okay. Now, at default, if you import in a component, right, or you import in a part into an assembly, right, it has 6 degrees of freedom, right? So I'm going to show you how to actually calculate the degrees of freedom, and then we're going to calculate the degrees of freedom for this engine we actually just assembled. Okay. Now, the three degrees of freedom are three translational relations, and then three rotational relations. All right. So basically, the three transitional relations they actually move across the x, y, and z direction, and then the rotational rotates around the axis of the x, y, and z. Okay. So I'm going to share my screen, and then we're going to just understand it properly. Okay. Okay, let me know if you can see my screen, please. Can you see my screen?
Yeah.
Okay, all right, thank you. Now, what we are going to do is this. We are going to analyze degrees of freedom using this simple method, okay? Now, this part, when you import your components into SolidWorks first, it's fixed, right? So when I say it's fixed, it means it's 100% completely defined, right? So you don't have redundant mates. What do I mean by redundant mates? These are mates that, like, they should be important, but they can actually be neglected. Okay, SolidWorks helps. What it does, people don't really pay more attention to it, but what SolidWorks does is this: it actually helps you. It removes the unnecessary mates. Now let me explain. Now we'll take 6 cases. Okay, now the first case is when there is no mate applied, right? In between these two objects, objects, right? These two objects, there's no mate applied. So basically, this object in question has all complete 6 degrees of freedom, right? So basically, it has its up and down motion, it has its x motion, and then its axis y motion. Then it has its axial on each axis, right? Complete. Good. Then so basically, it has all 6 degrees of freedom. Now, let's take an instance one, right? Where we meet an edge. If we make an edge, meet an edge to a face. Now, when we meet an edge to face, we end up having what? We end up having only 1 degree of freedom removed, right? We only remove 1 degree of freedom, and then the 5 of them. Okay, sorry, no, that's not edge and mate face. Sorry. So edge to face removes 2 degrees of freedom and then leaves 4. All right. So it's easy to explain now. Using with this diagram, the rotational movement about this C axis is not possible, right? It's not possible with this object. And then translational motion between the X axis here and here is not possible. If I'm to make it normal, right? So the motion between this axis and this axis here is not possible anymore. So basically, we only restrict two, actually just 2 degrees of freedom, and then we are left with 4 degrees of freedoms, right? Good. And then let's try another case. I'm going to suppress this. So let's try another case. Let's try vertex rather with face mating. Okay, this is a fix, and a vertex is an edge where lines intersect. Okay, so I'm going to take this vertex and I'm going to mate it to this face, right? I'm going to make that concentric. Now, with the vertex and mate, only 1 degree of freedom, vertex and face, only 1 degree of freedom is restricted. Everything else goes. Everything else is actually allowed, right? So only the X movement between this direction and this direction is restricted, between the vertex and this direction. Everything else from rotating on this axis, everything else is allowed. Okay? Then it can move up and down also. Then it can move this way and this way. So they are all allowed, only this motion is restricted, right? Good. Now, let's do vertex to vertex, okay? So rather, vertex to edge. Let's do vertex to edge first. This vertex, right, to this edge. Make concentric. Perfect. Now, for vertex to edge, you end up having 2 degrees of freedom removed. Okay. Now, if you notice, irrespective of which is being removed, you should know it doesn't even really matter the amount that is removed. You notice that the motion being removed quite varies, right? So now for this edge, you can't move it up and down. the up and down motion is restricted, and then the x, so basically the z motion is restricted, and then the x motion is restricted, right? Good. Then let's do we've done face to edge, right? Face to edge motion. Okay, do let's do vertex to vertex. So vertex to vertex would be this edge and then this edge. You can pick any edge you want. Okay. Now with the vertex to vertex selection, you see that we lose almost, for vertex to vertex, we lose 3 degrees of freedom. We remain only 3 degrees of freedom. Now we lose all translational motion and degrees of freedom, all translational motion, yes, and then we are left with all 3 rotational, right? So basically, it doesn't move up and down, but it can actually rotate on its axis, right? Perfect. Now let's try edge to edge, edge to edge, right? Then for edge, I select this edge and I select this edge. Now for edge to edge, you notice we are left with only 2 degrees of freedom. 4 of them becomes constrained, right? We lose 4 degrees of freedom and we are left with only 2. We're only left with moving here and rotating around the same axis, right? Only here and here rotating about its axis. We lost the rest of the motion. So it then brings to mind the idea that your motion, whatever you're applying your mating into, right? Whatever you're applying your mating should be with purpose. Okay, for me, I think this is the clearest representation of this. Then let's try the last one, face to face, face to face mates, right? I take this face and I take this face and I make them coincident. Okay, now for the face to face, we only lose 3 degrees of freedom and 3 are left, and we lose 2 rotational motion and then 1 translational motion. So you can move here up and down, we can move up and down, we can move here and here, but it can't go towards the x-axis, and then you obviously cannot rotate. You can rotate towards the x-axis, but you cannot rotate towards the z-axis or the y-axis. Okay. So now with this, I think this is the perfect representation of degree of freedom as far as it goes. Now, degree of freedom plays an important role, especially if you're working with okay, yes, robotics. If you're working with robotics, right, it's very quite important to understand the fundamentals of what you're doing. So if you are now applying motion study to your design, it becomes much more easier. Now, for example, let's check the how many degrees of freedom we have in this system we assembled. Okay, the system we assembled. First things first is to make sure it's actually working properly, right? As you would expect it to go. Okay. So I'm going to create a new motion study. Okay, watch carefully. I'm going to keep it at a default. Let's keep it here, right? And then also another explanation for motion study, right? Motion study in terms of creativity in SolidWorks after visualization. I think motion study comes first before visualization because a design might be good, yes, but as an engineer, you should be able to present your work in a way that non-engineers should be able to understand. Okay, you can explain to me the working principles of a four-cylinder internal combustion engine, and I will understand perfectly everything you mean. I would even want to chip in, right? Because I'm an engineer, okay? But then if you're trying to actually pitch to businessmen, CEOs, people that are not really engineering inclined, you have to not just so that you don't now we now have the true motion study where we can now simplify the explanation, but also increase its technicality. Okay, so more like making it easy for the layman to understand. So what I'm going to do is this. First things first is I'm going to add, since we're making real life, I'm going to add my gravity. I'm going to look for, now if you notice edge, notice at the edge, I've not selected any direction. I'm going to look for a direction that points downwards, not the face, an edge. Now, so my gravity is pointing downwards as it should. And then the value for gravity is constant. It's universal. You notice it's a global variable, 9.81 or 9,806, right? Good. I'm going to say okay. And then I'm not going to do anything else. I'm just going to change from animation to motion analysis, right? And then I'm just going to calculate. And I'm going to let it calculate. Okay. Okay. So now what I'm going to do is this now. What I'm going to do is this now. Then to calculate the degrees of freedom, wait, give me a second. Supply, excuse me. Okay, then let me see. Right click on my mates, and then I have degrees of freedom. So this dialog box now tells you in your whole system, it gives you proper details. Now you don't worry about the global count. The global count is basically an equation. The global count is just there to actually, more like your if you're working with simulation, your Navier-Stokes equation, it's more like the governing equation used to calculate the degree of freedom, an approximate degree of freedom. It tells you you have in this inline engine, internal engine, it tells you we have 46 moving parts. It tells you we have 53 cylindrical joints, and then we have 32 planar joints, right? And then it all calculates and gives you the total actual degree of freedom, which is 91. Okay, so at the end of the day, right? At the end of the day, you should be able to understand how your design actually translates to real life. Now, 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 for let's say, okay, I'm going to stop sharing my screen now. Okay, now for marine engineering, there are quite important factors when it comes to actual building. Okay, now for instance, degree of freedom plays a pretty important role in this selection. For instance, your the marine environment is a high risk environment, right? That is to say, anything goes wrong, lives are lost. Okay, that's normal. Good. Now, if you build an engine and without the proper understanding of the degrees of freedom of that engine as pertaining its internals and then its environment, right? You then stand the risk of having excessive vibration, which when if you know vibration resonance, the vibration where your machineries and then the engine and the machineries and the whole vibration now sync, and then it causes a crackdown where the where your what's it called where your actual vessels then start having issues. Okay, so at the end of the day, these play important roles in actual real life. This is just one single example. And then okay, in a factory, right, in a factory where you have to where you have to actually place your components or your machines with proper spacing, proper alignment and all that. And then if you're also using MATLAB, right? And you are actually let's say you are trying to calculate the efficiency of said engine, you should be able to know the amount of moving parts in this engine. You should be able to know the amount of joints in this engine. You should be able to know the amount of the degrees of freedom in this engine. All right. So for motion analysis, you can calculate the number of degrees of freedom from this. What we can tell now is we can calculate the number of freedom, and then we can as well as the redundancies that were introduced by the mates. Okay.
So thank you, Joseph.
Okay, then I'm going to be brief about the toolbox and the standard parts. I'm just going to say that it it is important to understand the core concepts behind designing, right? The purpose of you designing, you're not just designing for designing's sake, okay? You're designing for manufacturability, ease of maintenance, and then you're designing, sorry, excuse me. So you are designing with the intent that my design, somebody is going to actually manufacture this. So you now have two options. It's either you're designing to be creative. I do that most of the times. These are designs that wouldn't necessarily translate into real life. They are imaginative designs. Yes, you just build and then you don't really check stuff like measurements like the mass. You don't check the surface area. You don't check the volume and all that. You just build and then then there is actual designing where certain parts has to be built to standard. Right now, where SolidWorks helps is this. For most of I've been freelancing for a while now. Most of the designs I do has to be manufactured, right? And then if we have components, let's take an example. I was working on a silos design, right? And then this silos design, we needed about 200 bolts because it was layer upon layer. So we needed bolts to actually go. So I was not thinking, and most of the bolts we now had about like 25 of them separate, just little variations in these bolts. And these were bolts that should be able to get from the market easily, right? So that brings in the concept of standard mates, standard parts. For standard parts, these are parts that are inbuilt in SolidWorks. The main idea is productivity and efficiency, right? So decreasing the time it takes for you to actually start customizing each component, design custom components like ball bearings, bolts, washers, nuts. These are actually standard. So if you want to make the manufacturing process much more easier, you cannot go on and start what do you call it? Start customizing each part, right? Good. So you now have the option, we now have the option, a whole lot of option of choosing from different standard parts out there. And now the most interesting and I think the best part with SolidWorks is that we now have it contains a much more broader standard. So each company works with different standards on its own. Most companies works with IC, most study works with ISO. It depends on what your company is working with, right? But with SolidWorks, you now have a whole lot of options to choose from, whether you are Indian, based on what you're working with, or you're American, or you are African. So depending on the standard your country works with or the company you're working with, especially, it's very important, especially if you're working on remote jobs, right? If you're working on remote jobs, okay, then you then so it supports basically all the international standards you actually need. Then another powerful tool is this customization. Remember I said we should not customize, right, all components. Now I'm also saying that customization is allowed in a sense. That is to say, for your SolidWorks standard parts, if you alter your SolidWorks standard parts, let's say you had a situation where you should have molded it and then you let's say you were working on a creative process, not a standard design, a creative design, and then you instead just needed a bolt and then you just scaled it up or some sort, right? Then you scaled it up or you edited the actual master and design. The only way you get it back is if you know how it was before, you go back and correct it, or you would have to uninstall your SolidWorks, right? So basically you'd have to be careful with the master. So if you're editing a master, you should not forget to use options like save as, so as to save them separately in a separate folder other than your default folder. Okay, then take this from me. Standard parts in a design is not optional, right? It is very, very important, especially if you're working on manufacturable products. So basically, using the toolbox increases your productivity and reduces your modeling time, and mind-numbing, mind-numbing and repetitive designs, right? These are what makes engineers make mistake. You just get so bored and then you just, so what it does, it takes that off your chest. You can now just insert, you go there, and then you can customize your design tree for which you want to be which you want to show first and all that. So in professional engineering practice, standardization is really not optional. It's essential for efficiency and then reliability and global compatibility, especially if you're working on companies around the world. So your toolbox is much more than a convenience. It's not really just that, it's there for you to use. All right. Thank you.
Okay, thank you, Joseph.
Then lastly from my end, we'll talk about the common mistakes and how to avoid them. As far as design goes, the sweet and the good thing about SolidWorks is if you make an error, it won't hesitate to tell you you messed up, you made an error. And that's one of the most important. So your first constructive criticism comes from the SolidWorks diagnostics tools. Immediately you make an error, it tells you immediately, right? So even with powerful tools or advanced features, mistakes still happen in design assembly, right? So the software is intelligent, sure, but it only responds to the logic we actually apply to it. So at the end of the day, if our constraint strategy is weak, if your assembly method is weak, you end up having issues. So one of the most issues, common issues, is mates over-defining mates in situations where you actually have to add. Oh, one of the errors that are quite difficult to actually unravel are motion study errors. Okay, if you're designing with a part or even assembling, the error messages that pops up are clear. You get it clear. You can even use your help tool. SolidWorks help is there for you to actually just go and check. It gives you a help on what to do. But if you're working with motion study and then you get errors, motion study, it becomes much more difficult and cumbersome to actually. You'd have to, for the most times, what I just do is I just opt for restarting the motion, right? I take it, okay, more, this is like a learning process, I just start afresh and all that, right? So at the end of the day, you just want to achieve your goal. Okay, then so if you over define a certain assembly and then you start applying a motor to a hand that you already fixed, you added an unnecessary mate to it, you start having error messages. Then under defining, right? On the other hand, of a defining of components, that's still equally problematic. Okay, because when your part is not fully constrained, they remain floating in space. So this means they can still translate or rotate freely in one or more direction. Your degrees of freedom is not fully properly. You will now have, so you can't really tell which, because I was working on a robotic arm, right? For so and then I added a motion study to it, and then the whole joint started rambling off. Okay, I also remember I tried making the foot of this robot move, and then the whole mating on it starts detaching. So immediately I knew, okay, my mating strategy was just wrong. So I had to suppress every single mate and then start unsuppressing one by one and checking to see where I got the error. All right. So that's the answers poor mate strategy. You should there is no point most of the times your advanced mating can actually kill two stones with one bird, right? Your advanced mating can actually perform two purposes. Okay, so what you do is just immediately you use the most convenient, but at the same time you use the one that wouldn't give you issues in the future, like situations where you have to use concentric, and you could actually just use your with it feature to keep it middle. So you get what I mean. So that's what the idea behind So now every assembly should start with a fixed component base. Okay, this base is more like the foundation for the entire system. In real life, every machine has a frame, right? Housing or a grounded structure. So in SolidWorks, we replicate this concept by fixing one component in space. We fix it. So now every other design you're making, even in Sketch, if you're sketching a design, you notice your designs are always attached or restricted to the origin point, and then your design can be fully restricted. Okay, so ultimately, you have to understand now that engineering is not really about just clicking random uh, applications, right, or constraints until the model stops moving. So it's about thinking mechanically and actually applying your thinking and then a good strategy on how you want to assemble said process. Now, for instance, the design we did, the assembly we did, I could have easily now another example, I could have easily started first off with the engine block, then I bring in the connecting rod, and then I bring in the what's it called? I bring in the connecting rod top, and then I start assembling them there. But where I would not have issue is this. I would I would not have to replicate same process for each of the since it's four cylinder, I now have to replicate each process. You see, it takes longer time. But so I just decided, okay, I'm going to actually assemble them as a sub assembly, import it into SolidWorks, the main master assembly, and then make it flexible. So that just and then I can now copy with Mate easily. All right. So that's one important. So an assembly should be constrained intentionally. Over defining causes conflict, and then under defining problematic creates instability. So the main idea is to have full control over your constraints and your design. All right, for real life application, you have to make sure your designs are safe. Okay. Okay. Wally will answer your question at the end of the session. All right. Thank you. So Ryan, please, you can continue. You're muted. We can't hear you.
It's clear now. Do you hear me? Okay. I will repeat. So, as we conclude our presentation, let's recap the essential takeaway. We have learned that understanding the interface simplifies assembly workflow. Also, we have seen how mates are more than just connection. They are a logic system for controlling motion. And the end degree of freedom must be managed strategically, avoid over-defining and under-defining assembly. Uh, like like Joseph, how he said, effective engineering is about strategy thinking, not just software clicking. So, also, we hope this session has inspired you. Our, our collaboration doesn't end here. We are committed to strengthening and collaboration between designer and engineering, exploding into more advanced topic and encouraging innovation through practical application. Our goal is build stronger, more connected engineering community. We are already looking forward to continuing this collaboration event with you next year. We'll see you at ARC 2027. Thank you for your attention. We are ready to answer your all questions. So if you have any question,
Okay, let me read your question. You said, my question is that I have sub-assemblies. Can I have sub-assemblies in SolidWorks? Example, in case of an assembly hinges that needs to be in another assembly. Let's say door for easy. Okay, yeah. If you it works with the same principle as this piston, right? If you are working on a door design, okay, and then let's say the door itself is a part design, but then the hinges are assembly designs, right? So the best thing to do is not to, you should not, what you should not do is this: you should not build your, what's it called, you should not build your hinge on an assembly then import your doors. That's wrong designing. Okay, what you do is you build the hinge separately, right? And then you create a new assembly, import in your door first, and then you import in your hinge, or rather your hinge first, since your hinge is going to be the stationary part. Then what you do next is this: you make it, because when you import it in, it's not going to be flexible, it's going to be rigid, meaning the mates you applied for your previous subassembly of the hinge itself is going to be fixed. So all you have to do is right click and then make them flexible. Okay. So when you make it flexible, you can then now actually just start designing. That's just the whole concept, right? And then you can actually just fix only the said component that you want to keep fixed on the wall, or you use preferably I would prefer you use axis and keep the axis fixed of the axis of what you don't have to do is turn on your temporary axis and then keep it fixed to the main axis of your design canvas. Right? I don't know if that answers your question, because let me explain it now. When you open your SolidWorks for the first time, your canvas is blank, right? You now have your feature tree, you have your top plane, you have your right plane. So you go to what's it called, reference geometry. You create a you select axis, select two plane axes, and then create one axis. The axis is going to cut the middle of the plane. So when you now import in your hinges, you can now turn on what's it called? You turn on your uh, temporary axis. So the axis for the circular part of that is, then you can just mate them to the fixed, right? Then you keep them fixed. Then since it's hinge, you just keep it fixed and then it works. Okay. Hope I answered your question. All right. So Usman said, hello everyone. My question is that I want to practice assemblies, but when I downloaded practice files from SolidWorks official website, it says it's a visual version because I only have two tiers. Is there any reference file which I can practice with? Okay, yes. The the only issue is this. The only issue is this, that yeah, two ways. First is this: you could you could I think the best way is to use grab card. SolidWorks is an ever evolving software, right? As an engineer, you should evolve with the software. Okay, so I understand most times you can, it depends on the one your laptop can actually take or the one you can afford and all that. But you should try your best to get the latest version of SolidWorks. 2026 already is already out. You can actually try that. But for cases where you cannot, to get models is quite easy. You should use a grab card, and then if you're searching, you should specify 2018. So it gives you 2018 or later models. So you can use and practice. But the honest truth is that your scope becomes limited. So you now have the duty, although you can learn that same way, you cannot have the duty of actually designing the parts themselves and then learning the assembly yourself, right? So you should look for YouTube courses or so that has a part and assembly. And you should not be scared of large assemblies. The way I actually learned SolidWorks was with big assemblies. Okay, and the people I've taught is the same process. If you come to me and you say you want me to teach you SolidWorks, what I do is this: I ask you if you know the fundamentals, that's fine. I give you a design that's about like a YouTube video that's about 4 hours to 6 hours, a whole design. So by the time you actually start doing it, before you actually have mistakes, correct yourself, and get that whole product done, you should be able to use the majority of the tools. and then you try it again and you try it again, and that way you get better. Okay. Then another option would be for you to actually look for someone that has 2024 and above. I think 2024 and above can step down. I think so. 2024 and above can step down. So you give them the import them, tell them to download the models for you, or you can just search the models, send them the link, they download it, and then they open it and save it as a 2018 version, step it down, and then you can actually just use it for your own practice. I hope that answers your question. All right, you're welcome. Okay, Isaac, I'm new in SolidWorks assemblies. Why is it always recommended to use faces instead of edges when possible? For like instance, we use the cylindrical meets, concentric meets with cylindrical faces. Okay, now you have to understand when it comes to design, there are multiple ways to actually go about a certain design. Okay, the best practice are when you say here of best practice, you know the best practice are always the most efficient, less time consuming, and most efficient. And you as an engineer, your design should be able, you should be able, a new designer, right, should be able to what's it called, edit or modify or work on your design. Now for concentric, I think if in the list of the standard mates we have there, concentric mates and tangent mates are the only mates that deal with circular bodies, right? You want to create a rotational body around an axis, whether the axis is visible or not, right? So you could use edges, edges work, right? The only issue is that edges change. Okay, now this is the issue with edges. Now, if you are designing like okay, like the recent design I did now, there were situations where I used edges, right? And then in the process of assembly, I see okay, these edges, this assembly, the extrude I used, it's especially when you're dealing with motion, it's now actually interfering. So SolidWorks, unless you turn on your interference, SolidWorks will tell you two parts are actually interfering. When I mean interfering, they are like more like phasing through each other. Okay, so but now in that sort of situation, I just decide, okay, I think I need to actually just cut out a certain part and then chamfer it so that if you're manufacturing, you don't know, okay, this space is left for let's say this the different length. Okay, now in that situation, if you had mated an edge, right? If you have mated an edge to that, if you mated that edge to, I use that edge for mating. When you cut off that part, when you go back to the assembly, you start having errors. It starts showing you errors of missing face, right? It starts showing you errors of missing face. So that's why it's much more better to use faces. And then, but cylindrical, concentric is the best and only, I think so concentric is the only way to actually join two cylindrical bodies. Another option would be for you to actually join the two axes of the two cylindrical parts, but that still won't actually give you the rotational motion needed. So the idea, if you check the meaning of concentric means circular. It's more like a rotational. Then for tangent is when you want to move a line or a straight or a vertical or horizontal object on a circular object, a circular phase one. Yeah, that works. Yes, in hydraulics and all that. So that's basically what the only place you use tangents and all that. So best practice. That's just the reason why we use edges to avoid is mistakes and then don't have issues when you start designing. Okay, I hope that answers your question. All right, thank you. Okay, so anyone has any question, please?
If there is anybody in Tunisia, we can response you in French or Tunisian. So we have no question. So thank you. There is contact information. Please feel free to research out to Joseph or me or connect with the Benin and South Tunisia SWUG. We are always happy to continue the conversation.
So, all right, then, thank you everyone for joining in. Uh, thank you for joining in. The link to the South Tunisia um SOLIDWORKS group has been dropped on the chat, so you should join, and then you should join these communities so that when you need answers to certain questions, you can actually have an easy place you can go, and then when there's a webinar or there's a certification drive or that, you can keep and stay informed. All right, so thank you guys for actually joining. It's been a pleasure. So we hope to see more of your designs, right? We hope to see more of your designs. Thank you for attending. Thank you.
Thank you to you, Joseph, and thank you to Benin SWUG. And thank you to everyone for your time and attention. On this screen, you will see the coach QR code. Go ahead and scan them to join our official WhatsApp and LinkedIn community. It's a great place to ask questions and share your work and connect with other SolidWorks users. Thank you.
All right, then I will do my best to upload. Will do my best to upload the videos, the session recording. All right, thank you very much, guys.
Thank you. Have a nice day.